Hi, I'm Vidya Prasad, and I'll be presenting our work titled The Transform and Perform Framework, Explainable Deep Learning Beyond Classification. This work was in collaboration with Ruud van Sloun, Stef and Elzen, Anna Vilanova, and Nicola Pezzotti from Eindhoven University of Technology. Deep learning has gained significant attention for its exceptional performance in various applications. These include low-dimensional tasks such as labeling or object detection. Yet, not all tasks have low-dimensional outputs. For instance, in segmentation tasks like facial feature delineation, complexity arises as the output size matches the input size. Deep learning also extends to these high-dimensional regression tasks such as image-to-image translation, like altering the hair color. This highlights its versatility across diverse applications. In all these applications, the traditional development process is often iterative and trial and error. Since these models operate as black boxes, relying solely on performance metrics without understanding the underlying decision-making process is not ideal for creating reliable solutions. Explainable AI plays a crucial role in enabling model developers to make this a more informed process. However, the challenge lies in the fact that not all deep learning applications have adequate support for explanation. Current VA research primarily focuses on low-dimensional classification tasks. While there has been some work to support object detection and segmentation tasks, high-dimensional regression ones remain relatively unexplored. We refer to these as high-dimensional to high-dimensional or HH problems. Existing work in this area primarily centers around GANs and lacks generalizability to all HH problems. Now, why is this gap a problem? Well, low-dimensional classification tasks lack certain challenges present in these HH problems, resulting in existing VA systems having limited control for analyzing models beyond classification. Our goal is hence to unify these applications through our Transform and Perform framework, or TNP, enabling the design of VA systems for deep learning model analysis with general applicability to HH problems. TNP offers guidelines for designing workflows and analysis strategies in new VA systems, as well as describing and potentially enhancing existing VA tools. Extending existing VA systems to HH problems presents several challenges. While the challenges of high-dimensional inputs have mostly been addressed in literature, the complexities of HH architectures and high-dimensional regression outputs are minimally addressed. First, low-dimensional problems have this compressed 1D layer at the end of the network to analyze. However, HH models lack this single compressed layer, making analysis of high-dimensional spatial features complex due to the curse of dimensionality. Additionally, the number of output classes in low-dimensional tasks is small. However, in HH problems, there are many output variables or pixels which can behave variably, like the local failure in changing the hair color to blonde hair. This makes it challenging to define what is correct and what is an incorrect output, leading to subjective judgments that need to be analyzed. Moreover, common methods used for the exploration of low-dimensional tasks like TSNE and grouping by classes do not readily apply to HH problems just due to the lack of classes. This complicates scalable data analysis, forcing users to explore various data groupings. Finally, studying input-output symmetries can support the understanding of a model's inductive biases. For example, how does a classifier behave on rotation or reduced brightness of the main object? This analysis is hindered by unknown control variables, leading to unknown model behavior before user interaction. All of these challenges co-occur in these HH problems and just make it more complex. These challenges result in the users having to perform multiple exploration tasks, making the design of VA systems complex. To address these issues, we propose the TNP framework, which aims to facilitate VA system design by identifying workflows and analysis strategies suitable for studying HH models. We first define input-output relations to support our framework. Why? Well, the structure of a problem domain often influences the structure of the learned models, aiding in their interpretation. Hence, we extend Kindleman's algebraic visualization design framework to explore how changes in the input affect the model's behavior. We categorize input-output relations into three types. The first type is invariant relations, where the output remains constant even as the input changes. An example of this is when we apply small rotations to digit classification. The second type is equivariant relations, where the output changes in sync with the input changes, such as rotating a segmentation model's input. In contrast, models like those used for image denoising should ideally be invariant to input noise. However, deep learning models deal with complex input-output relations, often leading to unpredictable and possibly nonlinear output changes due to input variations. To address this complexity, we introduce a third category called generally variant relations to account for the nonlinear relations between inputs and outputs. This could also be the case for classification models. We build upon the works of Van Wyk and Keim as the foundation of our transform and perform framework, with a primary focus on model analysis stage. This stage includes components transitioning from a model-centric perspective to one centered on explainable AI and visualization. TNP primarily addresses how VA systems can aid in the model behavior specification component, facilitating model analysis with the 3 Ws, namely the when component, or identifying when the model behavior occurs, with a focus on model inputs and their ground truth. The next is the how and the why component, which focuses on understanding how and why a model behavior occurs, with an emphasis on model internals and their training parameters. Finally is the what component, which defines what the model behavior is, with attention to model outputs and performance. Designers have flexibility to define these 3 aspects and provide support for the 3 Ws. Through the Analyze Search Query component, designers can establish workflows across these 3 Ws to facilitate analysis. This component supports the exploration of the 3 Ws and their unknown relations previously described, allowing designers to analyze models. We introduced the TNP framework to assist VA system designers in studying HH models. So how can you, as a VA designer, put this framework into practical use? Here are the key steps. First, designers can begin by mapping their input and goals to TNP. We provide details of this in the paper. Once mapped, our method can be used to generate user questions or tasks, which are a blend of the 3 Ws: when, how, why, and what. Each question aims to understand one or more aspects of the 3 Ws while keeping the other components fixed or variable. Next, the type of analysis needed for each question must be determined. For this, we provide thought seeds and analysis strategies for each of the 3 W components and the input-output relations based on the challenges earlier identified. With the generated questions and analysis strategies, VA designers can focus their research process and design effective VA systems. In our paper, we illustrated how TNP can be applied by describing 2 existing systems and showing areas for potential improvements. Additionally, we also demonstrated how new VA systems can be iteratively designed using TNP, with a practical example in the context of medical image reconstruction. In summary, there is a significant gap in addressing HH problems in VA literature. Existing methods face challenges with applications with a lack of classes, architectural complexity, and handling high-dimensional outputs. The Transform and Perform framework has been introduced as a start to fill this void. It provides a unified approach to identify workflows and analysis strategies for the design of VA systems generalizable to HH problems. We've recently put TNP into practical use by creating a comprehensive VA system called Proactive, which we have just published in TVCG. With Proactive, we explore the unknown relations between inputs and outputs, enabling us to study model behavior globally. This approach is versatile and can be applied to tasks ranging from classification to complex HH problems. For more details, you can refer to our published work with a QR code. Thank you.